Hi everyone, my name is Dana Obanoff, and it's my pleasure to virtually welcome you to the Maurice J. Zucrow Labs here at Purdue University. As the largest academic propulsion lab in the world, we here get to do research in combustion, propulsion, explosives, hypersonics, laser diagnostics, and so much more. But rather than tell you all about it, I'll pass it off to some of my colleagues to show you around.
Hi, my name is Scott Meyer. I'm the Managing Director of Zucrow Labs. I did my undergrad and master's at Purdue and graduated in 90 and 92 and got to work at Zucrow a little bit at the end of my master's degree. I came back here in 2001 to work with the faculty and students to develop our test capabilities and all the different experiments that we operate here. Zucrow has a cool history. This laboratory was built for propulsion work. Our first building was built in 1948. Maurice Zucrow received the very first PhD that was awarded by Purdue in 1928. He went off and was working for Theodore von Karman as Chief of Staff for Aerojet Corporation when he was recruited to come back to Purdue to start education and research programs in propulsion in 1946. Zucrow set up shop in a Quonset hut building at the Purdue airport, and first experiments almost immediately burned it to the ground. So they decided, we're going to move you off campus. And so Zucrow Labs is located adjacent to the Purdue airport, about a mile off campus. And we have 8 laboratory buildings, all purpose-built for doing rocket, jet engine, combustion sprays, basically anything related to propulsion type experiments. We have reinforced concrete test cells with remote control rooms, just like you would find at many government or commercial laboratories. Our philosophy here is that the students that are working here are professionals, they are engineers, so they do all of the tasks. We follow the same rigorous procedures in the design of experiments, the design reviews, and the way things are built, and then the students manage all of that. In addition to the design work, they write the procedures, they wire their own cable harnesses, install their own instrumentation. Basically, they do absolutely everything. And so it's a lot of fun, it's a lot of hard work, but you get a lot of responsibility.
Hi, welcome to ZL1, where there's a lot of research that goes on in terms of laser diagnostics as well as combustion research. Let's go take a look. As a member of the Meyer Research Group, I work in laser diagnostics and especially combusting flows. Now what that entails is working on setups such as this, where this is a CARS setup, which stands for Coherent Anti-Stokes Raman Scattering, which allows you to use pulse burst lasers like this big guy right here, which send laser pulses in and can allow for us to measure temperatures in flames without actually disturbing them, because it is a non-intrusive diagnostic. So that's actually very helpful for combustion research, and a lot of that work goes on here in ZL1, in this room, and in another room that we'll just show you now. So this is the inside of a pulse burst laser that we use here at Zucrow Labs. Now what you do with a pulse burst laser is you take your initial inlet laser and you bounce it through all of these optics and you amplify it using, in this case, neodymium glass rods. And then by dumping a lot of energy into it, you can actually amplify your laser signal, and that allows you to get large amounts of energy compared to what a laser pointer will do, and that's very useful for the techniques that we develop here. So this is another room in ZL1 where we do explosives research with using laser diagnostics. We do the explosions here in this blast chamber, which allows us to do small explosive events. A lot of research we've done lately has been involved with detonators. And then what we've been doing with them is using devices such as this. This is a quad scope. Now the quad scope allows us to image something about here and split the view into 4 different views on the camera chip with this. And using those 4 different views, we can actually 3D reconstruct what we're seeing. So we can end up making evaluations of particle sizes using only a single camera, but 3D reconstructing it, which is actually a very fascinating subject called tone reconstruction.
Hi, I'm Jay Evans. I'm a second-year grad student in Aero-Astro Engineering, and I work at Maurice J. Zucrow Labs, or more specifically, the high-pressure laboratory, which includes ZL3 and ZL8. Just to orient you, ZL3 is where you met Scott Meyer and saw the rocket cell. It houses a lot of the original rocket cell and gas turbine test cell work that went on at Zucrow Labs. And then a couple years ago, construction finished in ZL8, where we have 5 new test cells and an all-new laser lab that spans the width of the building, where students can conduct even more high-pressure experiments and run diagnostics on them. Same kind of work, gas turbine and rocket-related stuff, or even more fundamental combustion, but more test cells and more modern facility space to do it in. All right, now we're walking into ZL3. So in addition to housing the gas turbine and rocket cell, this is also where a lot of the graduate student office space is. So you walk in. It's a pretty nice facility. You have a nice big conference room where you can have the big important meetings. I'll let Ethan kind of pan the camera around in there. And then on the other side we have professor offices, including Scott, who you met earlier. As we come further along, have a break room where students can eat lunch or interact, get coffee, things like that. Then coming further along, we have our cubicle farm space where students can do various things like CAD or data analysis. Anything that would require a computer, there's the workspace to do it in. So moving further along, there are collaboration rooms where various students are officed. Still more cubicle space. And then we start to get to the control room. So here's an example of one. We have a nice 4 monitor set up at each station with large TV screens to monitor the experiments as they're going on. Here's a bigger version with the rocket cell. And coming further along, this is where we start to get to where the test cells are housed. So you kind of have this intermediate hallway area where we're about to go to, where it splits off. We call the build-up area because students can do a lot of build-up tasks or maintenance on their experiments here. Coming along this way, here's what we call the locks room, but it's got more than locks in it, just the various propellants that mainly the rocket cell uses, but also some plumbing for nitrogen system control. Some more build-up space, and also the computers that collect a lot of the data from the rocket cell. And here's the rocket cell that Scott showed you, just to put it in context of where it is in the building. And then on the other side of this wing will be the gas turbine cell and the older laser lab. Hey Ben, are we good to go in the GT cell? Or? Yeah, you're good. Cool. And here's the control room for the GT cell. And right now there's a lot of build-up work going on in it, but here's the gas turbine cell, which is on the opposite wall of the rocket cell. And that is pretty much ZL3, and one major component of the high pressure lab.
All right. Hey there, I'm Charlie Black. I'm Eric Johnson. And we're both graduate students, master's students here at Purdue. I'm from South Carolina. I went to Clemson University for my undergrad.
I'm from Wisconsin. I went to Milwaukee School of Engineering for undergrad.
And we're both currently aerospace students here. and we're working under Scott Meyer here at Zucrow Labs, and we're doing testing on this RCS thruster here. So basically, we built up this whole stand with all the plumbing and tankage and everything you see behind it, and all the force measurement systems and all the instrumentation. And this is everything we learned to do here at Zucrow. And when we came here, we didn't have too much experience with this stuff, but we learned how to do it, and now we are in charge of this test campaign, firing this engine. So.
Okay, now coming from ZL3, this is ZL2. And we'll go ahead and walk in here and I'll explain what goes on in this building. So to this side of me are a couple test cells that largely they're doing hydrogen peroxide based work under the supervision of Scott Meyer. So a couple test cells here, and then further down the hall. At the very end of the hall is storage area, and past that are the compressors that power the giant air system we showed you by ZL8 earlier. What's really cool about this building is right down here we have an in-house machine shop with 2 machinists. And so students have the opportunity to get a lot of their components and parts machined in-house and to interact with machinists directly, which is not only hugely convenient for moving forward on your projects, but also to get that experience as an engineer of making a drawing, talking about it with the machinist right there, and working through those problems, and at the end of the day getting the part you need. So I would say that's one of the key elements of Zucrow that makes it unique and a good experience for engineering grad students.
Hi, my name is Julie Bach, and I'm a grad student here at Zucrow. Welcome to ZL4. This is the oldest building at Zucrow, and there's a lot of really cool stuff that happens here. There's some research on hypergolic materials, but a lot of the work that's done here is research into solid propellant materials. So let's go in and take a closer look.
Hey everyone, my name's Kyle. I'm in Dr. Sun's research group out here at Zucrow Labs. So today we're in ZL4 doing some energetics testing. I'm currently working on a material that's photosensitive, so you can actually get it to ignite with light energy, such as a camera flash, a laser, various things like that. So what we're doing today is we actually have a camera flash that you would see in a professional photography shoot. So it's just a xenon flash bulb, very bright. And we have little 3D printed pieces of nano-aluminum PVDF, which is like a fluoropolymer, like a plastic you see in strain gauges all the time. So we're able to ignite these samples with the xenon flash lamp, and we're just measuring how sensitive they are and trying to get a good gauge on the photosensitive properties of these materials and what we can use them for in like practical applications. So you can run a test if you'd like. Alright. So we'll close the fume hood, it'll kick off bad gases here, but we'll see if we can get one to ignite. Cool. So that went off. You can see the very charred bulb. This is an example of being able to actually ignite something with just regular old flashlight.
Hi, I'm Alex, and even though I'm still a new student here at Zucrow Labs, I've already been able to help out in our 3D printing work. Here we have a variety of different printers that lets us print everything from traditional plastics to more exotic explosive materials. We're working with a new technique called VA3, standing for Vibration Assisted Printing, which helps use ultrasonic vibrations to print really viscous materials. Printing energetics is exciting because it allows us to really customize our material, and we're really excited to explore the new geometries and techniques that it lets us do.
Hi, I'm Brandon Montano.
I'm Joey Lawrence.
We're both master's students out here at Zucrow Labs. Right now we're working on an extrusion test stand for the application of energetic materials in the additive manufacturing with us.
And so what I've been working on and helping Brandon with is I've been programming different Arduino boards to control the linear actuator in the system. So what these boards will do in this code will actually control the speed and position that we're moving down onto these different materials with to help actually extrude. So right now we're just working on getting those duty cycles set and figuring out what speeds we're trying to print at.
And we're hoping to use this test stand to understand the different mixtures and materials that we have and characterize some of the different propellants that we're able to print here at Zucrow.
Hey, Kyle here again. We're now in the blast room in ZL4, which is where we do all of our explosives testing and a lot of our shock and shock reaction experiments here. So up first we have the frag box, which is where we do specifically all of our explosives testing. So we can load this up with small amounts of explosives and actually detonate experiments in here, which I'm sure you can see by the wall here is a kind of reminder of the explosions that go on here. So in this frag box, we can put in materials like RDX, HMX, PETA, and we can run all sorts of detonation experiments to measure sensitivity, detonation velocity, or anything else we could be curious to figure out from an explosion. So additionally, we have this big window here. We'll put glass slides in front of it, and we can actually get very, very, very fast cameras, some of the fastest cameras around, to look into the frag box and actually observe what's happening during these explosions. The second thing we have in this room is our gas gun over here. So the gas gun can shoot projectiles or flyer plates very, very fast and impact objects way down at the back end there. This is really useful for, like I said, shock reaction physics or experiments where we're really curious what happens when we impact something and send a really powerful shock wave through it. So we'll load up experiments there. I know we've done like experiments looking at what happens or what new materials can be formed when you shock something. And yeah, that's the gas gun.
Hi everybody, this is Aaron Afriat. I'm currently in ZL4 room 110, also known as the combustion room, and I'm here to show you the various kinds of experiments that go on here. So let's make our way here. So in this lab, we work a lot on 3D printing of propellants and explosives. Yes, you heard that right. And this is essentially a setup that will allow us to make our own filaments to extrude those propellants and explosives. Now let's move on to over here. This is called a Crawford bomb or a Crawford pressure vessel, which has optical access, which means that we can actually see the propellant burning and see what's going on around it. So we use a high-speed camera to image that, and the way we insert our propellant sample is using a plug here. So we have our little strand, and in this case this is a 3D printed gun propellant strand, which has introduced porosity, as you can see maybe, and we're trying to image the difference between how the porosity will affect the burning of the propellant. Essentially, this plug will screw in at the bottom of the bomb, and we'll see the strand from this optical window. So next we've got two other pressure vessels, also known as bombs, and this one is called a parcel pressure vessel, which does not have optical access, but you're able to get the pressure trace using a piezoelectric transducer. And finally here, we have a very high pressure bomb, which we'll use to essentially look at the pressure trace of gun propellants, specifically 3D printed gun propellants. This pressure vessel will go up to around 60,000 psi, and it is still being set up right now. So this is the result of the burning test that we just did with the high porosity sample. And as you can see, this is the ignition phase, and then the propellant quickly starts to combust and the burning becomes more convective, so it almost, in a way, explodes.
My name is Blair Francis. I'm a PhD student with Dr. Pourpoint here in ZL4 in what we call the GELS propellant lab. We do a lot of characterization of different propellants like hypergolics, which are shown here, which ignite on contact, solid propellants, and hybrids. We try to characterize what gives them their performance, how to make them safer and cleaner to be around, and ideally how to improve that performance even further.